Hello, hello. Good morning, good afternoon, good evening,
I,
everyone.
you have it all covered, Barbara. I think we've got it all. Yeah.
Yeah. Well, welcome everyone to another technical webinar from GMI. Um, I think this is a great topic that we're going to be discussing today, Bob. Thank you so much for being here today with us.
Yeah, my pleasure. And this is the first time most of our webinars have always been on international requirements and standards. And actually, Barbara was the one who said, "Hey, why don't we do something around U.S. requirements?" Even though we know we have a lot of people from overseas, there's always companies that are overseas that might be doing projects that maybe need to be executed around U.S. standards. So, yeah, we kind of thought maybe this would not be a bad idea to for those of you who are not familiar with the U.S. requirements, to kind of give you a little bit of overview on that and what the standards say and how it differs from maybe some of the stuff that you're familiar with in the IEC world, so to speak.
Mhm. Absolutely. So I think there's a lot of material to be covered. So should we just go ahead and start?
Let's do it. Let's do it. Let's get into it.
Perfect. So again, welcome everyone. Today's topic is NFPA 70 updates, equipment for hazardous locations, and API practices in offshore environments. Um, by now, I believe you guys are very familiar with the speakers today, but we have Bob Johnson, our key speaker. As you know, Bob has many years of experience in electrical installations in hazardous locations. He's also the president of Source IEX, which is a distributor partner for GMI here in Texas, as well as his instructor for the IECEX COCP, which is the Bob, help me out here, certificate for
Certificate of
competence.
personnel competency. Yeah, yeah. No worries.
Yeah, this word sometimes skip my mouth. And he is also an inspector. So he has a lot of experience, checking all those installations in hazard locations. I think for both, right, Bob, ATEX, ICX, as well as the North American installations.
Yeah, most of them actually today I'm at a client's location doing a final detailed inspection for an IECEX project, and so fortunately the folks here were able to allow me to use the little conference room and take a break for an hour to kind of do this.
And we really appreciate that.
Yeah.
And I'm Barbara Vasquez Isla. I am part of the GMI team here in North America. I specialize on intrinsic safety. So before we go into today's topic, I want to talk to you guys a little bit about GMI. As you know, GMI is a manufacturer of interface devices specifically for intrinsic safety and functional safety. These type of devices are typically utilized on emergency shutdown applications, fire and gas systems, burn management systems, high integrity pressure protection systems. And the sectors that we normally support our customers are in oil and gas, petrochemical, pharmaceutical. We have a presence globally. We are a Italian company, but we have several offices around the world where we support our customers. All our production happens in Italy. So we have a state of the art production where every single item is tested before we ship it out, as quality is a very, very important part of our manufacturing processes. As a global company, we have a wide variety of certifications. So, as an European company, we have ATEX. As an international company, we have ICEX. As an American company, we have ULFM for United States and Canada. We support Brazil within Metro, India with Peso, etc., as well as DNV for marine applications. So on our products, you will be able to see all these certificates on the same part number, which is a great advantage for OEMs companies where they build one system that ships around the world. And this is our portfolio. Again, we specialize on intrinsic safety. So we have intrinsically safe galvanic isolator barriers. For functional safety, we have safety relays, so SEAL3 relays. We have signal conditioners, also for SEAL applications, SEAL3 power supplies, thermocouples multiplexers, which are great for monitoring temperatures in faraway locations, making the installation more cost effective by minimizing the wiring. We have SEAL3 hard multiplexers, SEAL3 and intrinsically safe surge protectors, as well as termination boards with our X1, which is for marshalling solutions where we minimize the space required to have all this galvanic isolation between your DCS and your field wiring. This is just showing some of the companies that we currently support, some of our partners who we support on their projects. Hopefully you can see your company there. And if you're not there, hopefully we'll be working with you soon. So now, Bob, the microphone is yours.
All right. Well, thank you so very, very much. I've got to stop my emails from coming in during the presentation. So, as Barbara and I were talking about this yesterday when we were kind of putting the finishing touches on this, there's a lot of information here. So we're probably not going to be able to get through everything. So we will, but don't worry, for any of you who are, here, you'll get a copy of the presentation. But what we were talking about doing is actually next month, or whenever we have our next one together, we'll kind of have a part 2, if you will, associated with this presentation, because there is a tremendous amount of information, and it was kind of difficult to pare down to a 45, 50-minute type presentation. So just be aware, there's going to be some stuff that we're not going to be able to kind of get into as much, but we'll try to get through as much of this information. And really, this is hopefully some good relevant information, a little bit of historical information, why we do the things we do here in the United States as opposed to some of the international requirements. So again, in the U.S., we basically follow, for the most part, the NFPA 70, or people call it the National Electric Code. And this product, if you will, or the NFPA document, comes out every 3 years. So actually, we're working on the 2023 version right now, and the 2026 version will be coming out here sometime later on this year. And Canada operates on what they call the CEC, and the same thing. It goes through a 3-year code cycle review, if you will. And so a lot of the electrical details, not just for hazardous locations, but all of your wiring requirements or electrical requirements are located within these documents. Within the NEC, the area in which we really focus in on is all in section 500 of the NEC. That's where we get all the bread and butter information with regards to hazardous location installations and details. Within the CEC, it's all in Part 18. So kind of a little bit about how it's broken down, if you will. So in the US and Canada, we really have 2 hazardous schemes that exist in the United States, or I should say, and Canada as well. We have our legacy system, the class and division system, and that's been around since literally the 1930s or so. Well, maybe not that old, but after World War, no, it was actually, I think the first class division introduction into the NEC was around 1940 or so. And I may be mistaken on that, but it's been around for a long, long period of time. Back in 1996, when the US decided to be much more involved in the IEC, that's when we introduced the zone concept into the National Electric Code, into NFPA 70. And more or less, we have left it up to U.S. industry to either stay with the division system or go with this new zone concept. And the zone concept within the NEC is very, very similar to the IEC requirements, but there are some national deviations. So the protection methods, installation requirements are all defined within the NEC. And again, in Canada, it's defined by the CEC. Here's the thing. The U.S., we use equipment standards developed by nationally recognized testing laboratories, which are approved and regulated by OSHA. So, for example, you might see a standard, and I think we reference it later on in this presentation, that there's an underwriter's laboratory standard for a test on explosion-proof enclosures. What defines an explosion-proof enclosure? And there's kind of a misnomer out there that people think, well, if that's a UL test procedure, then in order to get a certification on that product, that I must engage specifically with underwriters laboratories. That's not what that means. That means that UL took the leadership and the ownership of developing this standard, but the standard was written by members of industry, including other organizations outside of underwriters laboratories. So I sit on one of the UL committees, but I'm not a member of UL. But other nationally recognized test labs are also members of these committees. So when a standard gets published by an organization such as UL, that means that UL has published the standard, but other organizations can actually test and certify products to that standard. Now, in Canada, they approve standards agencies through the Standards Council of Canada. So there are CSA, for example, can develop standards. There are other organizations that will develop Canadian standards. And again, in the US, UL is not the only one, but they're the most common organization that has been writing US standards for many, many years. But when we actually go through and start looking, we peel back the onion, you can actually see organizations like Factory Mutual has developed some standards for US installations. IEEE obviously develops standards for US installations. So there are other organizations and standard writing bodies that are out there, but basically the testing laboratories all must be approved by the Occupational Safety Health Administration, which is our health and safety organization at the federal level that governs all this. Go ahead, Barbara. So some different examples, as I mentioned, UL, FM, there's Edison Testing Labs, which is actually owned by Intertek. You'll see an ETL standard. And again, these standards involve the equipment design and equipment requirements, and then also the testing procedures to verify the suitability. Excuse me. So when it comes to a facility here in the United States in particular, including new ones, we can now continue on with the class and division concept, or we can move towards the class and zone concept for area classification. I know when way back in 1996, when the zone concept was introduced within the NEC, there was a huge rush for manufacturers to start getting their products certified, both for class division and class zone, assuming that industry would just automatically start shifting over to the zone concept. But that never really took place. A vast majority of our facilities here in the United States still follow the division concept. However, there is a means in which products that are suitable under the NEC for class zone can be used in a class division area and vice versa. And that is spelled out within the NEC in Articles 500. So the scheme defines the equipment acceptable and so forth and so on. So the NEC, it is an installation standard. So probably the closest thing that you would say that would mirror this, for those of you who are familiar on the international side of things, is the 60079-14, or it may be that in conjunction with a general wiring regulation, such as maybe in the UK BS 7671, I think it is, or 78, 71, 76, 71. I may be mistaken on that one on the digit. For example, in Australia, they follow AS 3000, which is their wiring regulations. So the NEC, or the NFPA 70, is truly an installation standard. And it doesn't provide guidance on the manufacturer of certification of the equipment. Now, it does provide what is called industry accepted best practice and safety guidance for all electrical installations. And the chapters 500 through 506 are of the standard, details of protection methods, installation details, and wiring requirements for hazardous areas. And actually, it should be 500 through 504, if you will. 505 and 506 was added to the standard in the 1996 edition to align the U.S. with IEC standards And again, we use pretty much the same markings and standard practices as what we follow in the IEC-EX scheme. So things like gas groups, T codes, EPLs, all of that information is now part of the same marking scheme that you will find for products that are certified or listed, I should say, under the NEC in Article 505 under the zone concept. So the addition of 505 created these different hazardous zone schemes. And again, 500 deals with class and division methodology, which again is primarily used. 505 and 506 were basically our zone concepts. So for gases and vapors, that information would be located in 505. If we're dealing with combustible dust, we deal with Chapter 506. And it has not, however, generated wide acceptance or use except in the marine and offshore industries. Um, so the zone concept has been adopted here in the United States by certain clients. Most of those clients have been primarily in the offshore oil and gas industry, but on the onshore facilities, refineries, chemical plants, petrochem, it's still primarily around the class and division concept. So chapters 501 through 503, those detail the installation requirements for various hazardous environments. And 504, details the installation requirements for intrinsically safe. Now, the good thing is under Article 504, if you look at the installation details and you compare that versus almost every other standard that talks about the installation of intrinsic safety, it's very, very close. It's almost identical. So things like separation between IS and non-IS. In the IEC world, we talk about a 50 mil separation. In Chapter 504, we talk about 2 inches because we still like using inches as opposed to millimeters. So things like using light blue cables, that's also referenced in Chapter 504. So a lot of the similarities between what you would do on an intrinsically safe installation in the international world versus an intrinsically safe installation here in the United States, it's very, very, very similar. Now, what's interesting to note is remember this, that we are a republic of 50 states, if you will, here in the United States. And for those of you who are not familiar with it, well, we have the federal government and we also have our state laws and rules and regulations. And the federal government is responsible for federal regulations, whatever's written in the Constitution of the United States. Well, things like electrical safety is not spelled out within the Constitution. So the rules, or I should say, the actual who are the enforcement arms are really left up to the states. And it's up to each individual state to determine exactly what is the requirements for electrical installation in their particular state. And this chart is somewhat interesting in the standpoint. If you look at this, this is actually showing all 50 states and the adaptation of which version of the National Electric Code they're actually following. Now, this is a little bit dated. This was from December of 2022. But if you notice on there, you see a little KS and an IN. That's Kansas and Indiana. If we actually looked as of December 2022 in the state, if you were doing electrical installations, you would actually follow the 2008 version of the National Electric Code. So just because the NFPA updates the National Electric Code every 3 years, what's really important to understand is if you were doing a project, for example, in Texas, well, they were following the 2020 version, and that's good. But you have to pay attention to make sure that, hey, if we're going to do a project in another state, we just have to make sure that we're following the right edition of the National Electric Code. For example, for hazardous location, a lot of changes aren't made too terribly dramatic from every code cycle. So there's not big differences. However, there was a big change within the NEC in the 2023 version that all of a sudden allowed for example, a marine shipboard type cable to be used in onshore installations. And that was added into the National Electric Code in 2020, actually in 2020. Now, that was a new thing. And again, if I was using a marine shipboard cable for an onshore installation, like an onshore drilling rig, that's perfectly acceptable in the state of Texas. But if I went over to Louisiana and Louisiana was only following the requirements of the 2014, well, guess what? It's not in there. So that's where you have to be careful if you're doing a job or a project in various states. You have to understand that every state may have different versions of the National Electric Code that they follow. And the last thing about this that is important to understand as well, the National Electric Code, or NFPA 70, is a baseline. It's ultimately up to the authority who has jurisdiction in each territory, state, county, or city to determine exactly what they will accept. And in certain areas, they will have requirements that are above and beyond what's actually published within the National Electric Code. So the NEC is kind of a benchmark level, so to speak. But in certain areas, there may be requirements that are above and beyond that you have to make sure that you comply with. So it can be extremely confusing when we're dealing with projects in the United States. So in the NEC, we have different what we call classes, and we use the term classes to identify the type of hazard. So a class one hazard is where I use to identify an explosive gas or vapor. A class two hazard is used to identify combustible dust. And then finally, class three hazards are used to identify solid particles, or what we might call flyings or fibers. So class one is certainly probably the most relevant for most of the people on this webinar. If you're in the petrochem industry, if you're in the oil and gas industry, most of the hazards are going to be gases and vapors. However, certainly if we're in the pharmaceutical arena or in the grain elevator or plastics or something like that, those are considered to be class two. The class three type hazards, you might find these in process facilities where they may be using them for fibers or fabrics, where you might find the issue with solid particles, or even wood processing facilities. That's typically considered to be a class three hazard. Now, within our classes, we subdivide them into different groups. And there's actually a total of 7 groups, and these are used to identify the ignition properties of the hazard. In the NEC, Group A is the most volatile group. And we only have one gas that actually is a Group A gas, and that's acetylene. And Group B is the next most dangerous. It's slightly less dangerous than acetylene. It's slightly less volatile. The representative gas in that one is hydrogen. And then C and D gases are the vast majority of the vapors that you would typically find in process industries. So things like ethylene, propane, gasoline, these fall into the group C and Ds. For those of you familiar with the international side of things, we have these letters somewhat reversed, where a 2C gas in the IEC world is actually a combination of both acetylene and hydrogen. A 2B gas is actually considered to be a representative gas by ethylene, and a 2A gas is actually considered to be propane. So sometimes when we're doing teaching of classes, when we have people come in and they have to kind of get the gas groups correct, you have to kind of flip the numbers or flip the letters to make sure that if you come from the NEC world and you're doing IEC, you just have to remember that the letters actually mean something different. And unfortunately, we didn't use the same letter system that the international world did. So we have it, but we have it broken down into 4 different gas groups. So under the zone concept, however, what we have done is that we have adopted exactly the same as what in the international community has, where we have 2A, which is considered to be gases such as propane. 2B is the next most dangerous, again, represented by ethylene. And then again, 2C is considered to be acetylene and hydrogen. So what you might find down at the bottom, international requirements, what we may mark something is actually something like this, where we see a 2B plus H2. So what that is basically telling us, it's good for 2A gases, 2B gases, as well as hydrogen, but not acetylene. So that was actually a marking string or concept that was used or really kind of based upon the US when the international world really started looking at this separation of gases. Acetylene is one of those gases that's very difficult to build products to. For example, like a flat flanged flame-proof enclosure, we cannot build those enclosures to be suitable for acetylene, but we can make them suitable for hydrogen applications. So that's not uncommon. In the US, we would mark that product class one groups B, C, and D, stating that this product is good for hydrogen, ethylene, propane, everything except acetylene. Next. So, and one thing I've mentioned in here, we say API, which we'll talk about here in just a second, because there's another set of standards that are published, or I should say recommended practice, that have been adopted here in the United States, published by the American Petroleum Institute, that are very similar to the requirements based upon the NEC. So under the class and zone scheme, under Article 505, we use exactly the same temperature codes as under ATEX, IEC, EX schemes. However, for class and division equipment, we use a slightly different system that brings into play intermediate temperature identification codes. And we'll show you that here in just a second. So there's the legacy, or I should say the NEC 505, if you will, for temperature codes. And these numbers are exactly the same as what you would find in the international world. We break it down into 6 different T codes, anywhere from a T1 through a T6. And again, the numbers are exactly the same, thank God. So a T6 product in the international world will mean the exact same as a T6 product in the US. But this next slide, and this is something to emphasize, and this is true not just for US applications, but for international applications, the amount of temperature that it takes to ignite a flammable gas is not dependent on the explosive pressures of the gas. And where I'm saying this is that if you look at hydrogen down there at the bottom, hydrogen is a T1 gas. And if we looked at our T1 temperature rating, that was 450 degrees C. That means that hydrogen has an ignition temperature of something above 450 degrees C. So you think, okay, well, hydrogen is very difficult to deal with. It is, depending on the pressures, but from a temperature standpoint, it's not nearly as difficult to deal with as some of the other gases. You will see on the far right-hand side carbon disulfide. That's, I think, the only gas vapor that's out there that's actually a T6 gas vapor. It's very rare in industry, but it has an ignition temperature of about 90 degrees C. Most of your flammable gases and vapors will be rated T3 or better. So if you notice on this slide, most of them, if you have a T3 or better, or I should say they have ignition temperatures of something above T3, meaning that the selection of products, when we get into that, as long as we have a product that is rated T3 or better, meaning T3, T4, T5, or T6, they would be suitable from a temperature standpoint. Now, here's a bunch of different other T codes. So this is our legacy temperature codes that we follow within the division concept. And notice that we have the same numbers, and they represent the exact same numbers. So T1 is 450 degrees, T6 is 85. However, notice that we have intermediate temperature identification codes. And there was a particular reason why this was introduced in the United States quite some time ago. And actually, if we go to our next slide, I think, Barbara, this might explain it a little bit. So if you think about heat-producing devices that you typically would find in a typical refinery or chemical plant, the types of devices that generate a lot of heat are typically lights. Transformers, certainly, motors could, but lighting was always a big issue with regards to our facilities. So what you would find when we started introducing high-intensity discharge lighting in our facilities, we found that these temperatures of say, a 175 watt mercury vapor light, would generate a fair amount of heat. And it might be too hot for some particular vapors and gases that we might find in industry. So, under pressure from industry, the National Electric Code introduced these intermediate temperature codes to further break it down because there's a large jump between T2, which is 300 degrees, and T3, which is 200 degrees. And so these intermediate temperature codes were brought into play to allow us to use higher wattage, high intensity discharge type lighting. Now, why was this not really a big issue in the international world? Was because in many cases, the choice of lighting was typically linear fluorescence. And linear fluorescence typically operate much cooler than a typical high intensity discharge type lamp. Now, fast forward to today, most everybody is going with LEDs. So we don't have necessarily these intermediate temperature code issues like we used to, because LEDs are operating typically much cooler than you would find of, say, a 150 watt high pressure sodium or a 175 watt metal halide type lamp. So the whole idea of these intermediate temperature codes was really to address higher wattage lighting for use in hazardous locations. And again, with the technology changing, it's not quite as an issue as it used to be. Now, there's also in the international, or I should say in the US world, you'll hear terms like NEMA ratings. And sometimes people ask, what are these and where do they come from? So, NEMA is an organization, it's the National Electrical Manufacturers Association that came out with a standard years and years ago that came out with a designation for enclosures as far as their suitability for an environment. This is called the NEMA 250 standard, if you will. And it was very much adopted by industry here in the United States. So sometimes you'll see charts that will talk about ingress protection and how they compare versus NEMA. And they're very similar, but they're not identical because NEMA standards also talk about things like the corrosion resistance materials of the particular product, where the 60529 really focuses the attention primarily on the ingress of liquids or solids. There are some sections, however, in the 60529 for IP codes that do address corrosion, but the NEMA document, if you will, really expands upon that greatly. So you might hear a term about a NEMA 4X enclosure. And a NEMA 4X enclosure is basically very much a watertight and a corrosion resistant type material. So it has a higher level of against corrosion, like what you see here. There's also what you might find a NEMA 4 enclosure. So the type 4 enclosure and the 4X enclosure are basically built to the same requirements as far as ingress of water or dust. But when we make it 4X, then we mean that that enclosure now maybe might be in a stainless steel material as opposed to a carbon steel. It's protected against corrosion. You'll see things like in the hazardous world, they may call out a type 6 type enclosure. That's actually like a temporary submersion. It's very similar to an IP67. The other areas that you'll see for NEMA ratings, you'll see something called NEMA 7, NEMA 8, and NEMA 9. So a NEMA 7 is basically what an enclosure is considered to be a hazardous location enclosure. So you might find things like an explosion-proof box on there will actually say it's NEMA 7. So a lot of us U.S. engineers use that terminology. If you see that on a specification, it's basically if they say we want a type 7 enclosure, then they're basically asking for an explosion-proof enclosure. If they ask for a type 9 enclosure, that means that that enclosure would actually be considered to be a dust ignition proof type enclosure. So we use some of these NEMA terms in relationship to the construction of the enclosures. And sometimes people wonder, where does this come from? Well, now you know, National Electrical Manufacturers Association and industry adopted this. And even the NFPA has adopted these nomenclatures and will be called out in various sections within the NEC.
We have a question, Bob,
Yeah.
regarding a comparison between NEMA 250 and UL 50E.
Yeah. So NEMA basically gives the definition of what should be the actual performance of the product. The UL has developed specific tests to test the products, and that is the details. So, in effect, right, um, the if you look at the IEC 60529 for ingress protection, that's actually telling you the performance characteristics of what this product, and then it also provides details as to the testing procedure. The NEMA 250 basically kind of gives you a little bit of broad strokes. It's kind of defining it, and it does give some performance, but it doesn't go quite as deep. So UL Underwriters Laboratories developed an additional testing procedure, and that 50E was an example of a specific test. And then in that case, you could say that that product, if you tested it to that UL 50E, you would meet that requirement, and whatever that UL 50E test was for, you would mark that on your product and go that route.
Got it.
It's a little bit funky, but that's kind of how it works. So in the US, we have our division concept, as we talked about. We have our Division One and Division Two. So instead of the international world where we have the three zones, we have two divisions. So Division One area is that where we say a flammable gas concentration may exist in normal operation as a result of expected maintenance or repair or leakage. We call that a Division One. A Division Two area is that area in which maybe process is handled, process stored, but it's not going to be there under normal conditions. It would only be there under a rupture or failure. So if you really think about it, a Division One in comparison to a Zone Zero or Zone One is basically somewhat of a combination. Division One, in effect, is a combination of Zone Zero and Zone One, where Division Two is basically very, very similar in concept to what we would consider to be a Zone Two environment in the international world. So it's a very similar concept. And again, that's kind of a little bit more of a definition of that, the class and division. So if we kind of think about it, and this chart somewhat gives a graphical indication of how we somewhat classified. In the international world, we somewhat define it by hours. In the North American world, we typically have not. It's more been a classification. We don't necessarily use an hour type time frame, but when we break it down, we really can subdivide Division One into what we would consider to be a Zone One and a Zone Zero type environment. And again, Division Two and Zone Two are pretty much identical with regards to the duration and opportunity for that flammable gas air mixture to be present. So this chart is a little bit interesting, and we were chatting about this a little bit. The percentage of hazardous area locations or installations. If we look at North America and we look at the rest of the world, what is the majority of our hazardous locations? In the United States and to an extent Canada, although I think the ratio in Canada is slightly different. But in the United States, basically most of our facilities are somewhere between 5 and 8% of the facilities are classified as a Division One. And if we broke it down into zones, it would be literally probably about 1% of those applications are Zone Zero, and maybe 6 to 7 to 8% would be considered to be Division Two, with the vast majority of our installations being Zone Two or Division Two. We look at the international side of things, you'll notice that, again, very small percentage is Zone Zero, but we have a fairly large percentage of Zone One and almost a 50-50 split between Zone One and Zone Two on the international world. Now, again, these are generalities. This is not saying that absolutely, because every facility is going to be slightly different. But looking at it from kind of a big picture, why the discrepancy? Well, one of the things in the United States is that if you think about a lot of our petrochem facilities and you think about our weather, our petrochem facilities are typically outdoors and they have a lot of ventilation. We have large areas of land in which we can use these facilities. These refineries were built out in the middle of nowhere. They were outdoors, so we didn't enclose things. So therefore, we had a tremendous amount of ventilation. Therefore, our Division Two was typically much less. Also, because we had such large facilities, we could mount a lot of equipment outside of the hazardous location to where it would actually be considered almost non-hazardous. So, or we'd get it out of a Division One area and we put it into a zone or a Division Two area. So just by location, by the size of the facilities. On the other hand, in the international world, and again, this varies greatly depending on the industry and where it's located. But think of it this way. If we now take those same types of facilities and we shrink them down, maybe we don't have the large footprint that we can have a large petrochem complex. Maybe we have a much smaller facility and it's surrounded by maybe a city or an industry, not necessarily out in the middle of nowhere. Well, now all of a sudden we want, from all different kinds of environmental concerns, we want to contain a lot of these facilities inside of buildings or in structures. So therefore now we don't get the ventilation. And then of course, as we move further and further north, when we have to have facilities in which workers can actually do the work during wintertime or very cold temperatures, we're going to contain a lot of those types of facilities within structures that are actually going to decrease the amount of ventilation. So therefore, that's why we would typically find a greater percentage of maybe Zone 1 versus Division 1. So that's kind of the theory behind it, and that seems to be somewhat accurate. Now, within the United States, the division market and zone market, as far as how many people have actually gone to the zone concept versus the division concept legacy, it's a significant portion. Even though we've been doing this since 1996, 85% of the market is still in the United States around the division concept. The market didn't all of a sudden say we're going to go to the zone concept. They were perfectly happy with what they were doing. And so we've just kind of stayed that way. The markets that have adopted the zone market are primarily in places in the offshore market because they liked using the concepts under the zone concept, and also areas maybe up in, for example, in Alaska. Some of the original facilities up there, because they were contained, normally they would say that's going to be a Division 1 area. Well, if we now make it Division or Zone 1, we can use protection concepts outside of explosion proof or pressurized. We could use things like increased safety. So there are certain pockets within the United States that the zone concept is active, but again, a majority is still the division. Within Canada, however, when they introduced the zone concept, and they did that in 1997 within the Canadian Electric Code, they basically said any new facilities must be done around the zone concept. So they changed it. They said, you don't get a choice, Mr. Customer. You have to go to the zone concept. So Canada basically got rid of the division concept. And so any new installations that have been going on for the last 20, 30 years now have all been around the zone concept as opposed to the division market. So a little bit about the American Petroleum Institute, as I brought up before. And the API is an organization, the American Petroleum Institute is a organization that writes a tremendous amount of standards specifically for the oil and gas industry. And not just electrical standards, but all different kinds of standards. You'll see API standards for all different kinds of equipment that's used in the oil and gas industry. However, the recommended practices for hazardous locations were introduced way back in 1991. And the 505 recommended practice was introduced using the zone concept in 1997. And that dovetails right along with the fact that the National Electric Code introduced Article 505 in 1996. So API basically adopted that. Now, when you really look closely at what the API recommended practices are here for classification, it's very, very similar to what you will find in NFPA documents for area classification, except it's really geared specifically for the oil and gas industry. So API is very commonly used specifically in the offshore markets as well as onshore, but you will see this document as a basis for area classification. 500 will be area classification around the division concept, and Article 505 will be the area classification around the zone concept. So equipment markings. So API and NEC 505, we now mark these products and they will be marked in this fashion. We will actually say on a product that's marked in the US, we'll say class 1 and then we'll say zone 0, which means that it's good for all hazardous locations where the hazardous gas. A class 1 zone 1 product is good for zone 1 or zone 2 areas, and then class 1 zone 2 is good for zone 2 areas only. So in this case, this is an example of a product that is listed by, in this case, FM. And the reason why I know this is FM, you'll see a CSA on there as well. So FM and CSA are examples of two nationally recognized test labs here in the United States. But you'll see the little FM and you see a little US and you see an FM with a C. That means that the FM testing on this particular product was done both to the Canadian standard as well as the US standard, where the CSA did not have any reference to that. It just says CSA. We would assume that that was only done to a Canadian standard. So if this product was being used, it would be suitable for class division applications. It doesn't say anything about zone, but it may be further on the label that just got cut off. There you see that reference to type 4X. That's the NEMA rating that we talked about. So you'll see something like that. And then you see that it says Class 1, Division 2, Groups B, C, and D, Class 2, Division 2, Groups E, F, and G, and Class 3. One thing that you do not see on this, you don't see necessarily a temperature code like you would typically find on a lot of international products. I don't see a T code. Well, there's actually a stipulation within the NFPA 70 that you do not actually have to mark a product with a temperature code if that product does not have a relevant surface temperature that will exceed 100 degrees C, or otherwise a T5. So therefore, it's optional for these manufacturers to actually put a T code if, in fact, this product will not get terribly hot. So sometimes when we look at it from an international perspective, we don't see a T code. Well, that's the reason why. Now, here's an example of an enclosure, if you will. In this case, it was UL classified, and you'll see a UL on the right-hand side with a little C. That means it was certified to the Canadian market by Underwriter Laboratories. In this case, it said Class 1, Groups C and D, Class 2, Groups E, F, and G, and then also it says Class 1, Zone 1, Groups 2B. Now notice it does not say division on this particular product. It just says Class 1, Group C and D. If it doesn't say division on the label, that means it's default, it's good for both Division 1 and Division 2. So that's a little bugaboo that I don't like about our system, that it doesn't actually spell out and tell you specifically, whether or not I can use this in the Division 1 or Division 2, because the default is if it doesn't state it, then it's assumed to be good for both Division 1 and Division 2, which I don't like, but that's, I'm not God. So, but however, in the zone concept, we do have to put down the zone of use. Now, here's a different one. In this case, you'll see at the very top, we see that the normal ATEX marking, and that has Roman numeral 2, 3G, EX, NA, so forth and so on. And then we see down there below a UL with a US, and we see a Class 1, Zone 1. In this case, it has an AEX with an E, Roman numeral 2, Then it has EXE, Roman numeral 2, T5. So that AEX was basically telling us that that product was certified to the American EX requirements. If it just had the EXE, that meant that it was probably certified to the Canadian requirements because they did not require an A to be put in front of the EX like we do. Then right below that, we see our class division markings, groups, and then we do show a temperature range. And by the way, the standard temperature range for EX products here in the United States, if it's not marked, is the exact same as what we find in the international world, which is minus 20 to plus 40 degrees C. So some products you'll actually see that temperature range on there. In some cases, you will not. If it doesn't have it, then the default is minus 20 to plus 40. So that's kind of an example of a couple different requirements, if you will, for marking of equipment. They're putting it all together. So some of the protection concept that we recognize within the NEC, the zone concept, the 505, we use the exact same protection concepts, but in Article 500, we have different protection concepts, and they are similar and in some cases almost identical, but they are not identical in some cases. So we hear the term explosion proof. Well, that is a protection concept that we do recognize and use here in the United States. Same concept as flame proof, but it is different. Intrinsically safe is certainly a protection concept that we use in the international world. Purging, pressurized cabinets, pressurized buildings, we use that same concept. We also have something here called non-incentive. So that's referenced within the National Electric Code, and that's basically a lesser form of intrinsic safety. It's a low energy, a circuit that's incapable of igniting a flammable gas-air mixture. We also have what is called oil-filled, which is very similar concept to EXO. And we also have this concept called hermetically sealed, where we may seal a switch in a glass tube. This is a very common, or was a very common protection concept that we used for many, many years with push button stations. So these are some of the concepts that are referenced specifically within the NEC. So explosion proof, it does the exact same concept as flame proof. It quenches and contains an explosion, and we quench the flame. There is a big difference, however, between explosion proof and flame proof in the standpoint that explosion proof boxes has to withstand a 4 times pressure test, where a flame proof product only has to be tested to 1.5 times maximum pressure. And there are some other differences. However, the testing for explosion proof boxes is tested to the UL 1203 standard for explosion proof. However, if we were testing it to the North American standards for flame proof, we tested to a UL 60079-1 for flame proof enclosures. So there is a difference between the standards. In some cases, it's pretty dramatic, but the concept works the same. There's a higher level of safety built into an explosion proof product than there is for a flame proof product, but they operate in the same principle. Next, Barbara. So there are explosion-proof products that use plastics. This is kind of one of the first items that were out there that was introduced by a manufacturer years ago, using a labyrinth-type design for a flame path, even using plastics or ceramic-type materials that act as a flame path to cool off the hot flaming gases. So, but primarily, most of these enclosures are cast metal. We use cast aluminum, cast steel, cast stainless steel, very similar in concept and same materials that you would find in the flame-proof world. That you could also see something like this where you could have multiple flame paths in a single product. So you could have a flat flanged, you could have a threaded flame path, you could have a cylindrical flame path. Again, we use the same concepts in the international world as we do in the US world for flame paths. We just kind of package them slightly different. Again, all these flame paths are designed to cool off that hot flaming gas. Intrinsic safety, it works in the exact same level. There isn't really a IA, IB, IC within the class and division system, but intrinsic safety is a protection concept that is suitable for Class 1, Division 1, and Class 1, Division 2. Unlike in the IEC 8 takes world where we talk about descriptive system documents, generally what you would find and what's a requirement is a control drawing. And this control drawing is typically done by the end device manufacturer and found in the installation manual for the device. So, for example, if I was doing intrinsic safety in the United States, instead of me as an independent person creating a descriptive system document or Barbara creating one, this typically would be something that the end user, or excuse me, the manufacturer of the field device would actually provide this information and say, in order to use this particular device, we have matched this device against this brand of intrinsically safe barrier. And so there's a little bit more flexibility when we talk about it in the international world because, for example, GMI might not be on the list of manufacturers that this manufacturer is actually referenced in the control drawing. But if I'm creating a DSD on my own and I really like the GMI product, well, I could use that in the IEC world. Doesn't mean that I can't do it in the NEC world. It just means that, okay, I'm not going to do the control drawing from the manufacturer. I'm going to create my own control drawing, which would be basically a descriptive system document. And there's your associated apparatus marking, and this is straight off a GMI product, right? So you see that where we have the EX and the hexagon, that's all of our ATEX marking, our IEC EX marking with all the entity parameters. But right below that, you see there, in this case, it's listed for Canada and the US, and there's our marking for the US under the zone and division concept. So that marking strings, all those marking strings that you see down there, is basically telling us that it is suitable for gas, it's suitable for vapor, and we would install this in accordance to the control drawing that the manufacturer, in this case GMI, has actually provided you. So that's the information that you would typically find on your associated apparatus. Notice that the device, as Barbara mentioned, it's not a different device. There is no difference in the actual barrier itself. It's the same product. It just happens to have additional markings for both international as well as for the US market. There's an example of a typical control drawing that might be provided by, in this case, maybe ASCO. This could be an ASCO solenoid valve that they actually provide you this information. And then they will provide you the maximum parameters as far as the associated apparatus. And in this case, you would have to go and select the appropriate barrier to match up to that solenoid valve in order to maintain the safety. So, Barbara, I tell you what, I think we're right up against the clock here. Do we want to make
Yes,
this maybe a stopping point?
absolutely. A lot of information has been shared. So,
Yeah, for those of you who just joined us maybe a little bit late, we were looking at this and we realized, oh my goodness, we've got a lot of information that we want to cover, and we didn't really get into the installation details and how that's different. So what we are planning on doing is that we're going to have a follow-up webinar here in the next month or so. So make sure that you sign up for that. But if you cannot make it, that's okay, because these presentations are all on the GMI YouTube channel. So even if you can't make our next one, which we'll do the second part of this again here, probably in about 5 or 6 weeks, and we'll get into the details as far as installations, which will cover things like glanding, conduit systems, all of that kind of good stuff. We'll cover that in the next webinar. So we didn't want to kind of rush through some of this stuff because there is so much information, but we have enough there to kind of make this a little bit longer. So that was kind of what we decided to do here to kind of
yes,
address this.
and absolutely. And when the webinar is released, please sign up for it. Send us your questions as well. So we will have more time to go over that as Bob mentioned, we ran out of time. Uh, but yeah, I want to thank Bob for being here with us today, for sharing all this valuable information. And thank you for. Mhm.
Yeah, before we end, I know we may have like 30 seconds to answer a couple questions. So there was a question, what zone one and zone two, is there a standard? So the standard, the IEC standard for defining zone area, really actually the standard to really go into is the 60079-0. That's the general requirement standard, and it defines a lot of things such as definitions. As far as there was a question with regards to training, we do formalized training under the IECEX COPC scheme as well as COMPEX. So certainly reach out to me. I'll be happy to, answer any questions you might have. Uh, I think there was a question on IP requirement for zone one and zone two. The IP requirement or the standard is the 60529, and there are some minimum requirements based upon the protection concepts of minimum IP ratings, depending on the protection concept. And the last question, or a good question I want to answer here, was conduit entry devices on explosion-proof enclosures. Is it different than for EXD? Yes, it is. And this is a really important point. And this is why I want to answer this one. So on flame-proof products, the distance that's allowed between a stopping box or a seal-off on a flame-proof product is 50 millimeters. On an explosion-proof box, the actual distance requirement is up to 18 inches. And the reason why it's dramatically different is that the explosion-proof box is built to a 4 times pressure test, where a flame-proof product is not. And so when we add more volume into it by open conduit on a flame-proof box, we jeopardize the potential. We could very easily create a pressure piling situation, which could then rupture the enclosure or not provide enough cooling to make sure that we quench that flame. So there is a big difference. And then labeling, address the issue of equipment labeling, matching its contents during the webinar. Yeah, it's a great question. Uh, I tell you what, Alexander, drop me a note because this is a little more drawn out. So, yeah, good questions.
Perfect. Well, absolutely. I believe you all have our email address by now. So feel free to send us an email there. If not, on the website, there is a technical support form. If you send your questions there, it will come to Bob or myself. And yeah, we'll see you for part two.
For part two. Thank you so much, Barbara. And thank you, everybody, for participating today.
Have a great day. Bye, everyone.
Thanks. Bye bye.